I'd like to welcome all of you to the inaugural, is that correct, inaugural? Okay. Lecture on electromagnetics area. My name is Konstantin Balanis. I'm part of the faculty in electrical and computer energy engineering. It looks like we got more staff here than we have students. I wonder why we have more staff. Maybe the pizza, it's attractive. Anyway, we're going to let you know something about electromagnetic, which includes courses on antennas, microwaves, electromagnetic theory. So we're going to go through it. So what is electromagnetics? As I indicated though on the first bullet, is the study of the effect of charges at rest or in motion. You know, when you have electric charges, when they start moving, when they're at rest, we call that electrostatics. Of course, like 241 would be one which is primarily devoted to electrostatics. Then required course like 341 is when we have these charges in motion that create current, and we get radiation from that and so forth and so on. The basis of electromagnetics are four classical equations we call Maxwell's equation, named after Maxwell. I'll show you something about him, lived back in 1500s. So we call them Maxwell's equation. Actually, Maxwell, this was before vector calculus. He had 21 scalar equations. A couple of his colleagues, friends of his, once the vector calculus came along by Gibbs, they were able to take these 21 equations and put them into 4 equations, but in vector form. Now, they could have named those equations after themselves, but in honor of their friend Maxwell, they called them Maxwell's equation. Here's Maxwell, 1831 to 1879. As you can see, during that period, people did not live very long. Now, it's not just unique with him, many other ones. So if you do the math over there a little bit, you can see 40-some years old. Those are Maxwell's equations. You can see here they are in integral form. We also have them in differential form. And there's a relationship between the electric field and the magnetic field. The electric field is presented by E. Magnetic field is by B or H, as you can see it right here. So that's those are the bases of electrical engineering. Don't let anybody tell you otherwise. A lot of the things that we're doing in circuits. Circuits is a special case. No, really, this is the truth. The circuits, it's a special case of electromagnetic equations. When you take loop equations, for example, actually you even make an approximation. They're not the equations we use in circuits when we do loop equations for the currents. There's a term there which is left out because it's assumed most of these circuits equations that we use are in frequencies like VHF, UHF, where the wavelength is large. And usually the circuits themselves are small compared to the wavelength, so small that this other term that we leave out, it doesn't make that much difference. But they're not exact. Maxwell's equations are exact. So why electromagnetics? As you can see here, I was a little bit premature because I was so enthusiastic to tell you that electromagnetics here are the basis of electrical engineering. Fundamental and challenging problem. Wireless communication, special nowadays. Cell phones, and everything is wireless. Packaging, mobile units, like the cell phone. Look, a little small unit. You know, when the cell phone was invented, and he was electrical engineer, worked for Motorola. Yeah. Okay, they call it the brick, right? Now, he got the license from FCC in 1983, even though he invented it before, but he got the go-ahead in 1980. It was like 2.5 pounds, 1 kilo. If you go on the website, you'll see him holding in there. He's still living in California. And of course, look up from that small, look how small it is now, and all the things it can do. Who would people responsible for that? Mostly electrical engineers, people in electromagnetics and wireless communications. So the packaging, so many things going on. Antennas was one of them. Well, they used to be, the antennas were exterior. And then because cell phones didn't look that well with the antenna sticking out. Plus, they used to break. You put them on your pocket, sit down, it will break. So they moved it inside. They embedded inside the package itself. Stealth technology. We've seen the stealth aircraft. Who designed this? Electrical engineers, people in electromagnetics. Obviously, they had to compromise with the aerodynamicists because you're trying to make it as less visible to the radar as possible, but you had to fly. So we had a compromise, maybe between flying and visibility to the radar. So, besides that, other complex problems. All, especially nowadays with frequency moving higher and higher, microwave and maybe eventually millimeter waves. We talk about 5G, wireless communication. Maybe frequencies maybe even up to 60 gigahertz. Okay? So there are a lot of challenging problems, and those can only be solved if you use what we call full wave solutions. Full wave solutions or modeling is based on Maxwell's equations. And many other complex problems. Here I'm showing you some photographs. You can see here this F-117 stealth. In fact, one of my books, that's on the cover of the book. I got permission from the company in order to have that on the cover of the book. Here, the cell phone. Now, this is not of today's, maybe a few years ago. Base station, laptop, and what's inside. You can see some of the circuits that are within the mobile unit. Here's some of the older ones, starting off there. StarTAC. Anybody remember that? I had one. Okay. You can see, what is this? A little stub. That's the antenna. Here's another one. This is, those are Motorola. You can see the name over there. And then eventually they moved the radiating element, receiving element inside, internal. Like here now you see more of the modern cell phones. Here's the walkie-talkie over here. Here's the radiating element. This wire antenna, a stub, whatever you want to call it, outside the package. So, if you want to be one of the pioneers, make a pioneering contributions, and you want to specialize in electromagnetics, which again, I emphasize basis of electrical engineering. In order to be successful, what do you need to do? First of all, it requires a solid foundation in mathematics. A lot of as you saw Maxwell's equation, okay, they're firstly in vector form. So it has magnitude, it has phase, in other words, complex quantity, but in addition it has what? Polarization, direction. Electric field can be directed in different directions. We call that polarization. Most complex mathematics in electrical engineering are in electromagnetics. Okay, I'm thinking some of you that may have taken maybe 241 or about to take 241 or then eventually 341. I'll talk about those in a minute. So you got to be good in mathematics. Prerequisite to take courses in electromagnetics. Physics also. Some courses in physics are required to follow the pathways in electromagnetics. And of course, circuits as well. What are some of the prerequisite courses that people that want to follow the pathway area? All electrical engineers must take 241, even if you don't follow the electromagnetics area or pathway. You must take 202, obviously the physics, here's the physics, 131, 132 is a physics lab. But, so the 241 is the initial course, first course in electromagnetics that everybody has to take. Primarily is on static fields where the charges are not moving. There's no time variations. We call that electrostatics. So 241 is primarily devoted into electrostatics. There is a little bit of time variation towards the end of the semester. So that's the 241. Then we have if you want to take courses in the electromagnetics area, you must take 341 as the second semester, which is devoted primarily on time-varying electromagnetic fields. And we use the same book. Probably cover the first 5, 6, 7 chapters in 241, and we use the same book for the rest of the book. Well, in 341. Does anybody? How many of you have taken 241? Some of you are there. Anybody 341 yet? Oh, there we have. Okay, so you got a taste. You will, eventually. Highly recommend it. Obviously, you expected for me to say that because I'm in the electromagnetic area. But in some of the courses, even students from physics come and take it. We also have students sometimes go to the physics department to take electromagnetics as they teach it. All right? How about electives? Now, to take elective courses in electromagnetics area, you must take 341 as well, not just 241, 340. One of them, which I'm teaching this semester, is we usually teach in the spring semester every year. At least we offer it, assuming that we're going to get enough students to sign up for. But over the last 37 years that I've been here, we always teach it at least once a year. That's 443. Another one very popular, which again we've been teaching it at least once a year since I've been here, is 445 microwaves. And another one is 448 fiber optics. Those are senior elective courses in electrical. We teach all three of them. I believe even the 448 now, at least once a year. How about graduate courses? If you decide, and you should consider it very seriously, you go to graduate school. We have a number of classes you can see here listed. Now, in some places, and all those courses, by the way, they're also in the catalog. If you look at the electrical engineering catalog, you will see all those courses listed. Now, we don't list them there just to be there. We actually teach them, more or less on a regular basis. Some of them, towards the end of, not necessarily every year, maybe every 2 years, depends on the enrollment. But we list them there because we teach them. Some of them are taught almost on a yearly basis, once a year. Like, for example, 541, we usually teach it in the fall semester, and we taught it this past semester. All of those, again, require the 341. By the way, if you have any questions, you can stop me. We'll have also time at the end of it, but as we go along, don't hesitate. Graduate school. Now, of course, a master's, MS or MSc. MS requires a thesis. You take like 24 hours of coursework, and then you do a thesis. Now, the MSc, Master of Science in Engineering, you do strictly coursework. You have to take an exam at the end when you finish. Okay. Requires 30 hours of coursework. And then you take an exam, qualifying exam, at the end. So one with a thesis, the other one without a thesis. Now, the MS degree is primarily a little bit more applications-oriented. It's a good gateway course, let's say, or degree to a PhD. Although, Our department, our school here, allows you to go directly from a bachelor's to PhD if you have the grades. Okay, you have to be approved in order to go what we call direct PhD, from a bachelor's directly to a PhD. The PhD is a little more specialized. You select an area and you devote all your time. You do analytical work, experimental work, verification, comparison between the two of them. So it's a little more challenging, obviously, and it's kind of research and development oriented. If you have aspirations to become a teacher, to teach at a college or university, almost all of them nowadays require that you have a PhD. Now, they used to say that companies didn't like to hire PhDs. Master's degree was good enough. They used to say that because they didn't want to pay. You understand what I'm saying? Nowadays, almost many of the companies, take for example here locally, Intel, they're thirsty, they're hungry to find PhD students. I know they've hired many of mine and other faculty here in electrical engineering. Because a lot of the problems are more challenging nowadays, so you have to have a more advanced knowledge in engineering. Not just companies, but also government agencies. Again, as I say, academic institutions hire people with a PhD. Academia, of course, as I indicated, nowadays a must. You don't have a PhD degree, forget it, gone. Industry, government, I worked for the government. I worked for NASA back in the 60s, 1964 to 70. I started teaching full-time in 1970. I started working for them with a bachelor's degree. They used to hire bachelor's, master's, and PhD, and as they do today. All the government agencies, the advanced Lawrence Livermore Laboratory, Sandia Corporation in Albuquerque, for example. There are a lot of government laboratories, national laboratories. Lawrence Livermore were out in California, up near San Francisco area, San Jose, San Francisco area. So, what are applications of electromagnetic antennas, radio frequency, microwave communication, radar, remote sensing, all kinds of, within electrical engineering, we have a lot of specialties. Because you're electrical engineer, that doesn't mean you know everything about electrical engineering. IEEE has like 35 journals specialized in different areas of electrical engineering. That's how many specialties. Even within our department here, with our school, I shouldn't say department because we're a school, we have like 6 different areas. When we give qualifying exam, comprehensive exam, you have to select which are electromagnetics is one of them. Solid state, communications, signal processing, power area. So you understand what I'm saying? So even in our own department, you can see we have faculty which highly specialize in the different areas. We're not experts in the other areas. We don't know as much about the other area. That's why you're going to hear the next weeks coming up this semester from people talking about their own different areas in electrical engineering. How many we have, Cheryl? 5, 6?
You've got a few more to go.
No, I'm not talking how many areas, how many pathways, lectures that we have during the semester.
Okay.
You see, now I have to challenge. 6? You see, somebody's got the answer.
7 more.
7 more.
7.
Okay.
That's not all on areas. A couple are on like grad school.
Yes. I think we have, believe when we give a qualifying exam, we have like 6 areas, okay? Opportunities, companies, look at that. Even locally here, one of our biggest employees here for many employers, say for many years, was Motorola. Unfortunately, they went down. In Arizona, Motorola had 19 to 20,000 people employed. Where now it's General Dynamics, about 5 miles from here, Scottsdale. That used to be Motorola, Government Electronics Group. Okay, We got Intel, Honeywell. Used to be McDonnell Douglas in Mesa. Now it's Boeing because they were bought by Boeing. So many aerospace companies, Texas Instruments, IBM, Qualcomm, Broadcom, you name it. Many opportunities for electrical engineering, very diversified. It's another attractive part of the electrical engineering. You can almost find companies to be employed almost in any city. Let's say big city, major city in the United States. Government agencies, NASA, Army, Navy, Air Force. You can see a JPL, San Diego Corporation, Aerospace Corporation, and so forth. All right, now let's talk about a little more about electrical engineering. We have in electromagnetics, we have a facility which we built back in 1980s. I came in 83, we finished it about 1985. We call the electromagnetic anechoic chamber. As you can see here, there's a room. We have this absorbing material, which what eliminates echoes, reflections, because we want to create an environment with no reflections. Anechoic means anti-echo, no reflections. Unique facility. One of the top two in the university in the United States. The only other university has anything like that, and they've been around since the 1950s, was Ohio State University. They have a facility, which probably I consider to be number one in the country in universities. Ours probably is the second largest, and not only largest, but also equipped to be able to make very accurate and advanced measurements, both in terms of antennas, also in terms of scattering. We have some other facilities, a wireless communication lab, microwave labs, as you can see here. Here's another one, a laboratory to measure the electrical properties of materials, like conductivity, permittivity, permeability. Those are what we call the constitutive parameters which characterize a given material. Those are the three properties. Faculty. We have about 5 of them. Maybe in not too long from now, might be reduced somewhat. Dr. Eberly. Some of you may have already taken classes from him. If not, I'm sure you're going to see him. I'm second in line over there. Dr. Pillay, who's probably our, I got to use the right word. I don't want to say the oldest. I want to say the most senior faculty member. The reason is I'm second in order. So I don't want to say old. I want to say senior. You understand what I'm saying? No, Dr. Pillay's been here since, I believe, the late 70s. I came in 83, although I started teaching in 1970, but at another university. I was there for 13 years before I came here because I knew you guys were going to be here. So I wanted to be here when you were here. You understand? All right. Dr. Pan, he's been here a while. Came after me, I think in 1980s, and Professor Trikopoulos, you got to learn how to pronounce it, okay? You've been with us for the last 2-3 years, okay? And you can see it in parentheses here telling the university that they got the PhD degree. Let's see here, in case you don't recognize the name, maybe you recognize the face. Yes, Professor Eberly. This photo is from some years ago. If you see him now, everybody has long hair, okay? Area that he kind of specializes in research, although he teaches all the courses in electromagnetics, electrical engineering, plus some other ones like circuits and so forth. Here's Professor Trikopoulos. He's primarily interested in the terahertz frequency range. That's beyond millimeter waves. I don't know whether I don't recognize this guy. He had a makeup, I think, that day when he took the picture. So you can see some of the areas I've been involved with over the years, here and elsewhere. Professor Pan, some of the areas of research as well as teaching of interest. And here's our senior faculty member, Professor Ballet. If you decide to go to graduate school, you're going to come into contact with him. He's the director of graduate studies within electrical engineering. Here's some of the courses that he teaches, including, as I indicated initially, 448, senior elective course in fiber optics, lasers, and some of the other courses. Those are, again, some areas of research of interest to me. I'll show you some specifics here. One of the things that we're doing is, because it's very attractive, especially in stealth technology, is creating materials or structures and materials which do not exist in nature. In other words, they're not part of the periodic chart. But people, within the last 20 years, been able to synthesize this type of materials. They call them metamaterials. Meta means beyond. And we also we've been involved with this one, again, here personally within the last 7-8 years. And I want to show you some of the examples. One of the things that we want to do, as I indicate here, creating ground planes. Here's, for example, if you look at it here, this is a metallic, on this side, metallic ground plane. Okay, this is physical, has properties which exist in nature, all right? But we wanted to create one which has exactly the opposite type of characteristics. In other words, if we were to mount an radiating element of this one, we cannot put it right on the surface itself. It won't radiate. It would be shorting out. We call those type of conducting, electrical conducting surface. We want magnetic conducting surfaces which don't exist in nature. So we've been able to synthesize, like this is like a checkerboard type of a surface. Let me show you first the rectangular. You put some patches on it. Now you have to know how to, obviously, to design them. They have to be designed properly for the correct frequency. But here you can take elements and place them right on the surface. Why you want them right on the surface? Well, first, for aerodynamic purposes. You want to have something very conformal, not to create what? Drag, let's say, for aerodynamic. The other one is you don't want to lift it to be visible where? To the radar. We call those low profile. I will show you here. For example, like you want to create this kind of a structure that is not highly visible to the radar. We call that what? Stealth type of a target. So here's what I was saying is, if you want to take a radiating element like a wire type of an antenna, if you have a perfect electric conductor, metal, like this one, okay, you will not radiate if you put it right on the surface. It shorts out. Same thing if you have a loop antenna, very popular, or a spiral. Any of those. What you want is this, PMC. Now you can put that on the surface, but it doesn't exist. That's not part of the periodic chart. You understand what? We've been able to create it. This right here mimics, has properties of a perfect magnetic conductor. How is this created? And you take a substrate and you put a bunch of patches on them. I'm showing here rectangular, combination, rectangular, circular, different type of patches. It's a texture surface. Okay. We call that EPG, electromagnetic band gap. Now, this one here then, yes, it's a PMC, but only acts, that's one of the shortcomings, is not a PMC for all frequencies. It's only acts, has the properties of a PMC over a frequency range. That's what we call a band gap. Band gap means only works over a frequency range. That's the downside of such a structure. Where this one here, on the other side, is PEC for all frequencies, basically. All right, so here's a top view. And this is how it behaves. This is the band gap. This particular one was designed so it can operate between about 10 to 14 gigahertz. We actually fabricated one of this. We actually measured it in a facility. So, again, as I say, if you have plate like this, and you have a signal coming in from the radar, most of it will go right back in the direction it came from. Here it is. Came vertically. Most of the energy is in the vertical direction. So it's very visible to the radar. What we want to do is to what? Reduce the visibility. So now, I'll show you if we create a surface like this. All right? And in fact, it's a photograph of this one here. What it does, see, we have the signal coming in this way, but what happens? Redirects it away from the radar. See these 4 lobes, we call those lobes? The radar is in this direction. We send it away from it. We direct it in direction away from the radar. So we have a very low intensity signal going back towards the direction from which it came from. See? Time to show you. So the maxima are 45, 135, every 90 degrees. That's where the maxima are directed towards. Now you can create, of course, we can sit here and talk about all kinds. So here's another one. Instead of being square or rectangular, it's hexagonal. Same surface, type of a surface. As you can see, we call checkerboard surface. Now, you're not playing cards here, okay? But that's what we call it, checkerboard. That's the word is used. What does this one do? See, that's a photograph of this one. See, now we're creating 6 beams. Again, away from where the signal came from. So it becomes what? Less visible. Less visible to the radar. We call that stealth. So you can see what do we do that? We actually measured it. You see, you can think of it that maybe in your times, maybe not in my time, but in your time, you can have structures, airframes. We take here, because we've done a lot of work here. My group, we had a consortium of companies as well as government agencies for 28 years trying to work on problems related to helicopters. Boeing here locally, or what it used to be McDonnell Douglas, one of the members of the consortium. But we had, like I said, companies from all over the country, including NASA and Army, Navy. And this is a facility inside. So you can visualize, you can see that eventually you could have an airframe, like a helicopter, where the surface has nothing but those patches and become what? More stealth type of a structure. We're not there yet, but I think certainly it's going to happen. And here's another one. This is more simple. You say, put a loop antenna on the top of a checkerboard surface. Or, I have one of those right here. See? Actually, because the element is circular, it's better for the ground plane itself to be also have a circular geometry, like I'm showing you here. See, like this one. That's exactly a photograph of this one here. That is loop antenna right there. Or you can also put a spiral, as I'm showing you here. There's a spiral one. And we made it, we analyzed it, modeled it, analyzed it, made measurements, compared measurements with simulations, and we got an excellent comparison. Let's see if I have a, yeah. We were able to increase what we call the gain of the antenna as much as about, I'm showing here, this frequency about 2.6 dB, decibels. Actually, we got as high as 3. Okay. Here's comparison measurements and simulations of that kind of a structure. Measurement simulations. We do very well. This is the impedance. Here, the radiation pattern. Let's see what else we have. Here's another one, by the way, the same one, instead of being, because a lot of the airframes are not flat. They are curved. This one is, again, we have a loop antenna on the top of a spherical. This is just a portion of a sphere, a cap. Let's see. Anyway, so we can sit here and talk about some other examples, problems that we've been working on it. Again, you can synthesize the surface instead of have this kind of radiation pattern to actually be able to bunch the energy and be able to steer the beam in some direction that you want. You see, instead of being spread out all over, you're wasting energy in unwanted direction. If you want to send it in a particular direction, you say it takes the same amount of power and put it into a smaller direction, the signal will be more intense. Yeah, you can put it on top of a cylinder, as we're showing you over here. Those are some of the codes that we use. By the way, today, just about all areas of electrical engineering, simulations, computer, everybody behind a terminal. You could get them, go to their offices, everybody is working on the computer, and I'm sure you do the same. Well, some of the faculty here also had written books, okay, textbooks. I guess I'm one of them, and you can, I like to, this is now what are we saying? Advertisement, right? Toot your own horn, as they say, right? This is my 4th edition of the antenna book that we're using. Started first time in 1982. Over 2,000 universities are using this textbook. Okay? It's the 4th edition. This is the 3rd edition, was in color. This is the other book that I have in Advanced Engineering Electromagnetics for 541, 641, and so forth. Look what's on the cover. F-117. That we're talking about, this stealth aircraft. We have Professor Pillay has a book on fiber optics. Professor Pan also has one, what they call wavelets in electromagnetics. Okay, this is just with faculty within electromagnetics. We have other faculty in other areas that have written very successful textbooks. And this again, our pride and joy. I guess one more time, the chamber facility, very rare that you find in a university. Wow, requires a lot of space. Luckily, when I came here, university, we made a decision they're going to give us the space, to have, the room inside is like 60 feet in one direction, 27 in the other direction. I think it's 18 feet in height. It used to be Channel 8 before I came here. That's what it used to be. It's between the A and the B wing. Channel 8 used to be there before I came. So it was perfect, like they knew I was coming. Okay? No, this is the truth. It was, at least that's what I've been told. It was not Channel 8 when I came. It was before I came, maybe 2, 3, 4 years before. So we have a facility. It has a reflector over here, which in mid-'80s was costing about $250,000 then, mid-'80s. It was donated to us by a company from the Netherlands. It was shipped from the Netherlands, created and shipped by airplane here. We didn't pay a dime. It was donated to us by the company. Why it was donated? Nobody does anything for it. There's no free lunch, as they say, right? Well, the company did not have a facility in this country if they had a customer to try to sell this kind of reflector. And the deal was a win-win, as they say, right? That if they ever had a customer, they can bring it here and didn't have to pay for it. We'll show it to them. And indeed, they had two customers, one from the northwest part of the country, I think in the San Francisco area. Not only they brought him here, but also bought one, and another one was from the North Carolina, near Chapel Hill, Raleigh, in the Research Triangle area, as they call it, where the three universities, NC State, University of North Carolina, and Duke University are. Anyway, they came, they saw it in operation. We made some measurements for them, but they didn't pay anything because they made all these donations. I mean, the software that is needed to run this facility is about $50,000. Again, donated. Now, let me just tell you, closing here with a little, it's not a joke, actually happened, because I guess the CEO of the company, we got to know each other. We're good friends, and we wanted to update the software. He updated the software. We wanted an update of the software, and he wanted $50,000. I said, Joe, a CD only costs $1. You understand what I'm saying? I'll buy the damn thing. I said, I'll give you the CD. Well, I said, oh, Constantine, we can't do this like that. So we went out to had a lunch, a couple of beers, and guess what happened? No, this is the truth. I didn't even have to give him the CD. So I guess I bought him an extra beer, and I guess it made up for the CD. Anyway, it's up to date. That's the good news. And that's it. Thank you very much.